Hi everyone, my name is Atifan Pudin. This is a demo video of how classes will be done in the Learn Smart Academy. Today we're going to be demoing the Physics Chapter 1 of Unit 1, more specifically 1A, that is velocity and acceleration. Without further ado, let's get into it, shall we? Right, let's start off. Um, with velocity and acceleration before we learn. What we hope to do at the Learn Smart Academy is not to blindly follow a textbook, not to blindly follow the words that are there, the content as it is in brain, and feed it into your brain just the way it's there in the textbook. You don't need a teacher for that. What we want to do is to understand the core of it as students who've done the exam, who've excelled in that exam, to say the least. We know what are the core fundamentals of the unit, of the chapters that you need to know, and sort of the method you would have to use to understand something, or the sort of aspects of that subject you would have to fully comprehend in able to excel at your exams, right? So how we do that is to first and foremost read the learning objectives, have a look at your specifications, and understand what it is that the examiners expect you to know, right? So the learning objectives of this chapter, right? There are three learning objectives, right? The first one is to distinguish between what scalar and vector quantities are, right? The second one is to distinguish between speed and velocity, and then to define what is acceleration, right? A third one would be to calculate the values using calculate values of acceleration, of velocity, of speed using the equations that they've given to us, right? Calculate values using the equations given to us. So those are the sort of objectives that you would have to know in this chapter. So the relevant specification point would be that would be motions. So you would have to discuss about motions, unit 1 motions, and within motions you would have to look at the first sub point. That is the only point of the specification relevant here. I put it as a screenshot. It says be able to use the equations for uniformly accelerated motion, right? Important word here, uniformly accelerated motion in one dimension, right? First and foremost, let me explain to you what is meant by uniformly accelerated and what we mean by it in one dimension. It's pretty self-explanatory, but let me get to it very quickly, right? So we are aware that when, let's say, a vehicle moves, for instance, when you're driving on the highway, there is, when you have to overtake someone, you accelerate the vehicle, right? So accelerate is essentially talking about how quickly your speed increases. Uniform acceleration states that the rate at which your speed is increasing is constant. So let's say you go from 120 to 130 to 140, right? You go in that order from 120 to 130 kilometers per hour in 5 seconds, 130 to 140 in 5 seconds. This is essentially what uniformly accelerated means in this instance. And let's talk about one dimension, right? Again, very simple. So we know that in general speaking terms, we discuss and we talk about there being three different planes, there being three different dimensions, right? So x, y, z, right? That would be, that's how we have 3D objects. Essentially, when we're talking about this particular chapter, we'll be talking about it only in one dimension. So that would be, perhaps x or y. Let's say a ball moving forwards and then towards the right and then towards the left. So it's in that one plane, that one dimension, or upwards and downwards, right? So that's what we are talking about when we talk about one dimensional learning. When you move into your next chapters, you will learn how to integrate two different dimensions. If I'm not wrong, in unit 1 physics, you will not be learning about matters regarding the third dimension. I assume that's not there in any aspect of your A-level physics units. You don't have to worry about that, but this is what one dimension and what uniformly accelerated means, right? So let's go ahead with what your learning objectives expect you to learn, right? So firstly, let's move into a white color pen to make things a bit easier, clearer. So what is a scalar vector? Sorry, a scalar quantity, right? And a vector quantity, right? A vector quantity, right? So a scalar quantity is essentially, right, a quantity which only has a measurement. Let's take a couple of examples, right? So one example that we can use is distance, right? Distance is one that we can use. Another one that we can talk about perhaps is weight, is mass, right? These are the two easiest ones we can talk about. So let's talk about mass first, because we'll get distance later on. Its pair would be weight. A relevant vector quantity would be weight, and a relevant vector quantity for distance would be displacement. So let's talk about mass versus weight. So what is weight? And this is something easier, because when you stand on a scale, let's say you're 50 kilograms, right? This is your weight. While 50 kilograms is the wrong term, you want really 50 kilograms, right? It's just a relative term that they use. The reason we use kilograms is because it's a lot easier. It wouldn't make sense for it to say, I'm 50 newtons, right? So we use the word kilogram here in scales to make it easier. But realistically, when someone says I'm 50 kilograms, that describes a mass. So you wouldn't be 50 kilograms, you would be a certain value of newtons. Why? Because weight is relative to where you are. Weight acts downwards towards the earth, towards the gravitational pull. So there's a direction in which this quantity exists, and that would be downwards, right? Let's take mass on the other hand. Mass does not change regardless of where you are. It does not change whatsoever. Even if you were to stand perpendicular in a space shuttle, perpendicular relative to the earth, if you were to stand in empty space, in empty orbital, right? Not orbital, sorry. In a vacuum, if you were to stand in a spacesuit, your mass here, or even while you're standing on Earth would be the same, because it has nothing to do with direction, right? It does not change based on direction. It's just your mass. It doesn't change. The value of it doesn't change based on sort of direction that you are on, and there is no direction in which it acts, right? Now let's talk about distance and displacement, and talking about distance and displacement will lead us to our second learning objective, and that is to distinguish between speed and then velocity, right? Let me move into a new page. So let's first and foremost start with what distance is. Okay, let's take point A. Let's call that New York, because why not, right? Let's talk point B. Let's call that Texas, right? So you could go from New York to Texas in a straight line route, right? Alternatively, if you're adventurous, you could pay a nice visit somewhere in Canada. You could go like this, perhaps. Or you could take an alternative route, extremely adventurous, head down somewhere to Southern America, to maybe to Mexico, or to Brazil, perhaps. You could take that route either, right? So you have that option as well. Regardless of it, you're going from point A to point B. But let's say the distance of going the straight route, a straight route would be far shorter than to take a route that goes through either Canada or Brazil. And that's what distance talks about, just the value of the space between 2 points, regardless of and based on the sort of path you take. There is no direction, because you can take any path. So the distance is not a vector quantity. On the contrary, displacement is a vector quantity. It has direction. So from A to B, if we were to talk about its displacement, it would be the shortest possible distance between 2 points, and because it's the shortest distance, it's a straight line, and hence the direction of that straight line would be its displacement, right? So that's the fundamental difference between what distance and displacement is. Once again, to recap it all, displacement is a vector, and hence it has a direction, right? Distance, on the other hand, does not have a direction, And for that reason, to go from point A to point B, you could take a plethora of routes, a plethora of directions, and you could finally land in B. There is no one single direction, right? So displacement is a vector. It's the shortest possible distance between 2 points, A and B, right? And because it's the shortest possible distance, it is a straight line, and hence it has a direction. And I know New York and Texas probably doesn't look like this. It's something like I know the US is a ball, say I think New York is here and Texas here, if I'm not wrong. So the direction would be this. I know my geography wasn't the strongest in school. The point is, this is basically what you have to know about what distance and what displacement is. Now that you've understood what distance and what displacement is, you could then talk about what speed and velocity are, right? As mentioned earlier, speed is a vector, is a scalar value, whilst velocity is a vector value. So let's take the standard definition, the textbook mathematical definition of speed. The definition of speed is equals to distance over time, right? So we know that distance is a scalar quantity. Time is also a scalar quantity, because there's no direction for time. It keeps moving, right? It's just a value. There's no direction. A positive time or a negative time. Time is just time. It's also scalar quantity, and for that reason, speed would also be a scalar quantity. Again, taking the example of my dear New York and Texas, right? If I was to go through a path from Canada through Canada, right? My distance would be, let's say, I don't know, 3,000 kilometers, and I would take a lot of time, right, to travel that entire distance. Maybe that seems less. Maybe 36 hours, right? The amount of time it takes for me to travel that distance, the distance of 3,000 kilometers. That's how speed works. But velocity, the definition or the textbook definition of velocity is V is equals to S over T. S is the abbreviation, or rather the symbol for displacement. Don't ask me why we have S instead of D. I assume because when you do further mathematical questions, that the use of perhaps when you do more mechanics, you would see that displacement is used more than distance, a lot more. And when we have displacement and with D, I assume that they thought S would make more sense. I don't know why they thought it would make more sense, but for some reason thought it made more sense. Okay, without being pushed around the point, let's get back to where we started. So the displacement between dear New York and Texas would be perhaps 1,000 kilometers, a short distance, and the time, because it's a straight line, and assuming there's a bridge between the two and it's a straight line, a perfectly straight line, you could perhaps travel that in 10 hours. So your velocity would be a vector value. Why? Because it's measuring the speed between two to travel from one point to another, and that point from one point to another has a displacement and not a distance, a straight line. So your velocity has a direction. Your velocity would be in this direction. Your velocity would not be in this direction because you are not moving this way. It's moving a straight line. But on the contrary, if you would take speed, right, your speed cannot have a direction, because let's say this is point A, point B, right, and you're taking a route that looks something like this. Your speed here, right, different color, so your speed at this point, right, at this point and at this point would be the same, but however the directions are completely different. So there cannot be a particular direction for speed, but for velocity on the hand there can be a particular direction. Why? Because it's a straight line. It uses a displacement, right? Are we clear? I assume we are, because there's no way of me knowing this, because it's not real class. If it was, I would respond to you. Sadly it isn't. But let's move on to acceleration, right? For acceleration, it is a development of what speed is. So the textbook definition of what acceleration is, right? Acceleration, my handwriting is terrible on this. My acceleration is the rate of change of velocity. To comment on my handwriting, it's generally bad. There isn't too much difference between this and when I write on paper, sadly. Okay, acceleration is the rate of change of velocity, right? So what does this mean? The rate at which there is a change in velocity. That is what we are able to understand when we break down this sentence. So let's say a change in velocity. A change in velocity can be represented by delta v. Delta is a mathematical symbol, right? Is a mathematical symbol that we use to state that it's a change between two constant points. So let's say you have a particular speed, you're traveling 10 meters, and over here you have a speed of, let's say, 5 ms minus 1 meters per second, right? And over here you have a speed of 2 ms minus 1. Your change in velocity would be 5 minus 2, right? That would be what your change in velocity would be, delta v, right? So that is a change in velocity. Now rate of, how are we able to convert the word rate of into a mathematical definition, right? A rate is essentially how much something changes per second, how much of something happens per second. And how we define it by second is we divide it by the amount of time it takes for this change to happen. Let's say to go from 2 ms minus 1 to 5 ms minus 1, it takes you 50 seconds, right? So your acceleration would be 3 over 50, and that is my calculator. There you go, my trusty calculator. 3 divided by 50 would be 0.06 ms minus 2. Why is it ms minus 2? We know that the value for velocity is ms minus 1, right? Meters per second. So because that is displacement over time now, so it would be meters divided by second. So it's ms minus 1, and ms minus 1 divided by a second. So if you did math and if you learnt about I forgot what this term is, if you do maths, you would know that when we want to move s from below the division symbol and you want to move it on top, we can give it a negative power, right? So it would move from ms minus 1 to ms minus 1 multiplied by s minus 1, which is ms minus 2. That's how we get ms minus 2 if you wanted to know. So what does 0.06 ms minus 2 mean? Basically what it states is that the speed of the object increases uniformly, right, across 50 seconds at 0.06 ms minus 1 for every second. So let's say at second 0, at point 0, right, at time equals 0, it's 2 ms minus 1. At 2 seconds after it travels, it's no longer 2 ms minus 1, it's 2.12 ms minus 1. Why? Because it is increased by 0.06 ms minus 1 each second, right? So that is what acceleration means. It's the rate of change of velocity, and I've shown you an example as to how it can be shown mathematically. Yeah, so let's look at the next learning objective. The next learning objective is to use a set of equations. These equations are called SWAT equations. I know it's a weird name, but the reason we call it SWAT equations is because these are the terms that are involved in the equation. S is for displacement, U is for initial velocity, start in the beginning velocity, V is for final velocity, A is for acceleration, and T is for the time taken, right? That's what SWAT means. So let's look at the list of equations you've been given, right? Let me very quickly copy it from the previous one. Give me a second, guys. Right, here we have it. Okay, here are your SUAT equations that you need to know for your syllabus. So let's look at the first one. The first one is S is equals to, apologies, okay, is S is equals to U plus V divided by T over 2. So the displacement is equals to the final velocity plus the initial velocity multiplied by time divided by 2. Right, that is your first equation. U plus V is the first initial velocity plus final velocity. So if we were to just take it, S is equals to U plus V over 2. What does U plus V over 2 mean? The initial plus final velocities divided by 2. So that would be the average velocity across the period in which it's transferring, right? So let's say it's at 2 ms minus 1 here, and as it moves it becomes 5 ms minus 1. U plus V divided by 2 is 7 over 2, which is equals to 3.5 ms minus 1. So we could say that the average speed across its its movement or its travel would be 3.5 ms minus 1, and we multiply it by the amount of time it takes, right? Let's say 50 seconds, right? S minus 1 multiplied by S, these cancel off, so you would just have 3.5 multiplied by 50. That would be 3.5 multiplied by 50 would be equals to 175 meters, right? Let's look at another equation. V is equals to U plus AT. V is the final velocity, U is the initial velocity, A is acceleration, T is time. Let's say an object in a straight line with uniform acceleration moves from t equals 0 to t equals 5, and it has an initial velocity that we don't know, right? We don't know what the initial velocity is, but we know that the final velocity by the time it reaches this side is 5 ms minus 1, right? Okay, so we know, and we also know that it has an acceleration, we know that the initial velocity is 1 ms minus 1. We know the initial velocity, we know the final velocity, we know the time, but we don't know the acceleration. So we can just rearrange our equation, right? So 5 is equals to 1 plus AT, A multiplied by 5. So 4 is equals to 5A, A is equals to 4 over 5 equals 0.8 ms minus 2, right? And it's the same case for all these equations, right? V squared is equals to U squared plus 2AS, S is equals to UT plus half AT squared. These are multiple equations that you have the opportunity to use. Right. So my recommendation to you would be to sort of memorize these equations. And why I say memorize is, despite it being if I'm not wrong, this is available to you in your student booklet. I'm not quite sure, but even if it was available, I would still recommend that you have these equations by heart. When I mean by heart, for you to understand why we would use each equation, because if you see clearly in each of these equations, one of the components are is usually not there, right? So let's look at the first one. In the first equation, we don't have, let me get a different colored pen. We don't have acceleration. Here, what don't we have? We don't have displacement. Here, what don't we have? We don't have final velocity. And over here, what don't we have? We don't have time. So because of that reason, it's quite easy when you have equations in where you don't know one of the values, right? You don't know one of the values, you can simply use one of these equations to figure it out. Because let's say for instance you want to figure out the speed, but you don't know what the final velocity is, but you do know its initial velocity and the amount of time it takes. You can use this equation, S is equals to ut plus half at squared, because it's the component of velocity. Even though you don't have it, you can still find the amount of displacement an object moves, right? So that's the benefit of knowing all these equations by heart, because the sort of mathematical questions you'll be given in this instance would all be scenario based questions. So for that reason, it's always good to have an understanding. While they've given you the SWAT equation of S is equals to ut plus half at squared, this can also be interpreted in a different way, right? So if S is equals to ut plus half at squared, S is equals to Vt minus half at squared. This is an alternative equation to S is equals to ut plus half at squared, right? This is something that is not necessarily given in the textbook, but this is also an equation that we can use. So for instance, when the checks fit, when we have all these items but we don't have the initial velocity, we can use this. So basically, in the first, second and fourth, right, that's when we don't have acceleration, displacement and time. In these alternative equations we can use it when we know everything but we don't know either the initial or one of the either the initial velocity or the final velocity. We can use these pairs of equations, right? Keep this in mind. This is not there in the textbook, but this is something you can certainly use. Let us quickly have a look at some of the checkpoint questions before we end this in the class, right? The demo class. I hope to be seeing you guys more frequently after this, because all that we're doing right now is a demo class to show you sort of learning methods, the techniques we'll be using. We strongly believe in using visual guides and visual aids to teach kids, right? So when you see our next demo video, which would be on a practical, we can very clearly demonstrate to you how we wish to explain how practical works without necessarily skipping over it, because a lot of the times schools tend to skip over practicals simply because they are unable to do it. There is a lack of time and whatnot. We expect to explain to you and demo to you what even practicals are, right? So let's just move on to the checkpoint first, right? So let's look at checkpoint number which one looks interesting? Checkpoint 2. Checkpoint 2 on page number 11. It states that a driver in a car is traveling at about 40.2 kilometers per hour. So we know that we can model a car as a particle. So generally, before we move ahead, when we are talking about velocity and acceleration and whatnot, while it's not there in your textbook for physics, it's something that mechanics students are well aware of. We model these things as particles, and because we model them as particles, it doesn't have drag, right? When we're talking about velocity acceleration equations in this regard, we model these items as particles, and we assume that it doesn't have drag, because obviously we know that when there's drag there is a force acting opposing the motion, and because of that reason these standard SUAT equations won't work, because it realistically wouldn't accelerate the way we expect it to accelerate. This is something that you got to keep in mind. A lot of the times it wouldn't matter to you, but just we wouldn't consider these factors, because realistically an object would be slower than what they say here because of air resistance. So just keep that in your mind, right? Let's model this car as a particle, right? It's traveling on the road. Okay. It's traveling at about 40.2 kilometers per hour. So again, when you have equations in different values, so in here it would be kilometers per hour, and you would have seconds, or you would have meters. Always convert them into one single set of units, right? It makes life a lot easier for you, and you're able to answer the question adequately and correctly, right? A driver in a car is traveling at about 40.2 kilometers per hour, sees a cat run onto a road ahead. So a part of this equation exactly is to convert it from kilometers per hour into meters per second. How do we do that? Into meters per second. So immediately it's a matter of converting it into units, right? So it would be 40.2 multiplied by 1000. Why? Because a kilometer is 1000 meters. So if you were to calculate it from 40.2 kilometers to meters, we would have to multiply it by 1000, and we'll have to convert it from hours to seconds too. So an hour has 60 multiplied by 60 seconds, so that would be 40.2 multiplied by 1000 divided by 3600. Then we would have, let me do that math for you quickly. Right, we would have 11.17 meters per second rounded to 2 dp, right? That would be in terms of meters per second your speed. First part is done. Let's look at B. The car travels 16.5 meters whilst the driver is reacting to danger. What is his reaction time? So they say that he sees a cat run onto a road and the car travels 16.5 meters whilst the driver is reacting to the danger. So he is at, let's say, let's call this t equals 0 when he first notices the cat, and let's call this t1. We don't know what t1 is, and this is 16.5 meters away from it which t equals 0 happens. Now we know that car is traveling at about 40.2 kilometers per hour. So we've got to assume that, when they haven't told us, whether there is an acceleration or deceleration or whatever, because they don't say that he stops it. Reaction time is the amount of time it takes for him to reaction time is the amount of time it takes for the person to notice the danger. The stopping time is how much time it would take for him to decelerate. So we assume there is no acceleration or deceleration here. So what equation do we use? Acceleration is not given to us, right? It's not, we don't even need it. Acceleration is equals to 0. So which equation would we use, right? We would use S is equals to u plus v multiplied by t over 2, right? How would we use it? S is equals to, the initial speed is 40, is 11.17 ms minus 1 plus 11.17 ms minus 1 divided by 2 multiplied by t. We don't have to even do this. The reason we find the average velocity is to find when something is accelerating or decelerating. Hence that, because there is no acceleration or deceleration here, this is not even necessary anymore. We could just simply say what was the traveling distance, 16.5 meters is equals to 11.17 multiplied by t. T is equals to 16.5 divided by 11.17. This is equals to 1.48 seconds, right? We didn't even in the first place have to use this. The reason I used a sweat equation is to demonstrate the sweat equation for you, and to show you that because there is no acceleration, we didn't necessarily have to use this. Even if we used S is equals to, right, d over t, we would have come to the same, v is equals to S over t, we would have come to the same conclusion, same value. And let's see how that would be, right? V is equals to the velocity, which we know is constant, 11.17, and we know the time, we don't know the time, but we know the speed, we know the distance being 16.5. So for us to let me move into a new page and move the items along. 11.17 is equals to 16.5 divided by t. For us to find what t is, it's just a matter of cross multiplying. We move this onto this side and this onto that side, so we would have t is equals to 16.5 over 11.17, which would result in the same answer of 1.48 seconds. So the reason I use a sweat equation there was to show you that where there is zero acceleration, we would have the same values at the end of the day, right? Because there is no acceleration, there is no movement. Whether we used this or whether we used that wouldn't make sense. There we had to use the average velocity, because we could have used the average velocity. The average velocity is the same because there is no acceleration, right? So let's revisit what we have here, right? So we know the time. Time is equals to 2.5 seconds. We know the final velocity, v is equals to 0. We know u is equals to 11.17. Do we know the distance? S, we don't know. We need to find the acceleration. So which equation would we use? We would use v is equals to u plus at, because that's the equation that makes sense here, right? V is equals to u plus at. 0 is equals to u, which is equals to 11.17, plus a is the acceleration, multiplied by 2.5. So when we move it, minus 11.17 is equals to a into 2.5. Acceleration is equals to 2.5 divided by minus 11.17 divided by 2.5 is equals to minus 4.468. Now you might be wondering why we have it as minus. Now initially we took that the movement of the car would be in this direction, right? If it was a normal acceleration, its speed would increase in this direction because its velocities are in this direction. Now when it comes to a deceleration, right, the manner in which the velocity changes is that the velocity decreases. So that means if the velocity is decreasing, the direction of the acceleration would act in the opposite direction, no? So instead of it going higher and higher, it goes lower and lower. So the direction in which the acceleration acts is in the opposite direction. So let's say this what object do I use, right? This car over here, it's increasing, right? Speed increases. So that means its acceleration is increasing in this direction, right? But if you were to say that it's moving at a constant speed and then it starts slowing down, instead of it acting, its speed increasing this way, its speed increases this, its velocity increases this way. Although you can't see it moving this way, it is because the velocity is here, right? So if an acceleration is acting this way, right, first and foremost it would start to slow down and then only it will continue to move. If the acceleration continued, it would continue to move in this direction. So that is essentially what the deceleration means and why the deceleration is in a negative value. To recap it again and showing the model to you again, if the vehicle was to move this way in a constant speed and it starts to slow down, it's decelerating. Because if we were to assume that the acceleration was to continuously exist on the vehicle even after it stops, even after it stops, if the same value of acceleration was of deceleration was to act on it, the value, it would come pretty fast, start to slow down and stop, and the deceleration would continue to act on the same direction. So the vehicle would continue to speed up in a reverse direction, right? That is exactly why the deceleration is in a negative value. So normally in mathematics we would give, or when we're writing it, we write it with the arrows on top. So we show that v is in this direction, u is in this direction, a is in this direction. So for a, that is in this direction, so the acceleration in this direction would be in negative value because it's acting in the opposite direction. Why? Because acceleration again is a vector value. But if we were to write a, right, acceleration with the arrow pointed in the reverse direction, we could say the acceleration in the opposite direction would be 4.468 ms minus 2. That is it for what we have as of right now. To come in contact with us, you could check out our Instagram page. You could comment on this video. We should be able to make a Facebook page available to you soon as well. Through one of these media, you could contact us and we will let you know as to how we're having classes and how we're going to be starting. Also be subscribed to the YouTube channel so that you would be able to see more of our demos, and once we gather more teachers, and as mentioned, our goal and motto is students helping other students. So we'll be having a lot of student teachers, extremely qualified student teachers, who will be able to give you the same education at a much affordable cost and promote allowing equality for education amongst all kids. That is sort of our motto at the Learn Smart Academy. That's what we have in our mind, in any path that we're taking forward from here. So I hope you guys have enjoyed the class, and I hope you'll be able to understand it. I very much apologize for the background noise that you can hear. Unfortunately, I don't work in a studio. I don't have a studio for myself. So stay tuned. I hope you've enjoyed it. I hope you're able to understand what the first bits of the chapter is, and expect all classes to be of similar or much better caliber. Thank you.